Hello, my name is Sha Zhou. This is my first year of the Earth Institute postdoc program. I'm going to introduce my recent work, projected increases in intensity, frequency, and terrestrial carbon costs of compound drought and aridity events. Co-occurring soil drought and atmospheric extreme aridity have recently received more attention because they may cause significant damage to our society and ecosystems. Soil drought is generally represented by low soil moisture, while atmospheric aridity is usually represented by high vapor pressure deficit, or VPD. VPD measures the difference between saturated and actual vapor pressure, so it also reflects the atmospheric water demand. In terrestrial ecosystems, soil water supply and atmospheric water demand can regulate the opening and closing of plant stomata. Under favorable conditions, plant adjusts stomata to match water demand and water supply. But when drought and extreme aridity occur, water demand is far more than water supply. Plant stomata would largely close to reduce water costs, and the plant photosynthesis is also limited. So occurring soil drought and atmospheric extreme aridity would largely reduce ecosystem carbon uptake and may even drive widespread tree mortality. Large-scale atmospheric anomalies such as blocking and tropospheric warming can initiate climate extremes and may lead to co-occurring drought and extreme aridity. But our research finds that the compound drought and extreme aridity are mainly attributed to nanosphere feedbacks. As summarized in this figure, sustained soil moisture deficit induced by precipitation decline can largely increase sensible heat flux and cause extremely high temperature. Lower evapotranspiration due to soil drying will further reduce atmospheric humidity and increase VPD. VPD in turn further enhances evaporative water demand and may exacerbate soil moisture depletion. Additionally, soil moisture anomaly can also induce precipitation anomalies, which may act to amplify soil droughts. These nanosphere feedback processes can lead to strong coupling of soil moisture and VPD, and even drive widespread compound drought and extreme aridity events. This figure shows the observed coupling of soil moisture and VPD. We find negative correlation of soil moisture and VPD globally. The figure A is for land surface soil moisture and B is for root zone soil moisture. The negative correlation indicates that lower soil moisture tends to be accompanied by higher VPD. The importance of this soil moisture VPD coupling for the occurrence of compound extreme events is supported by the right bimodal distributions of soil moisture and VPD towards both extremes, namely high VPD, low soil moisture, and high soil moisture, low VPD. The high probability in the top left being of this figure indicates that the compound high VPD and low soil moisture occur more frequently than expected if soil moisture and VPD were uncoupled. In this slide, we use idealized simulations to assess how these nanosphere feedbacks contribute to the soil moisture VPD coupling and the compound events. In the reference simulation, soil moisture is fully coupled with the atmosphere, while in the experimental simulation, soil moisture is prescribed by preserving the seasonal cycle and long-term trends of soil moisture in the reference simulation, while but removing the sub-seasonal and interannual variability of soil moisture. In both simulations, the atmospheric model is driven by the same forcing, so the differences between the two simulations represent the impact of soil moisture variability on the atmosphere. Consistent with the observational results, we find the negative correlation between soil moisture and VPD globally, as shown in figure A. The bimodal distribution of soil moisture and VPD is also evident, as shown in figure E. This result indicates that the models with fully coupled soil moisture can realistically simulate the compound soil moisture and VPD extremes. However, the soil moisture VPD bimodality is not found in the experimental simulation, in which the VPD variability is driven only by the atmosphere. Without the feedback of soil moisture variability on VPD, the frequency and the intensity of extremely high VPD are largely reduced, as shown in figure B and C. The figure G further shows that the compound high VPD and low soil moisture events generally occurs more frequently in regions with more negative soil moisture and VPD correlations, indicating that this soil moisture VPD coupling can increase the frequency of compound extreme events. The soil moisture variability are largely induced by atmospheric dynamics, especially the precipitation variability. However, this soil moisture can also impact precipitation. Compared to the reference simulation, we find that the frequency of extremely low precipitation occurs more frequently in the the frequency of extremely low precipitation is greatly reduced in the experimental simulation. It means that this soil moisture precipitation feedback can greatly induce the extremely low precipitation and soil moisture conditions. This is because low soil moisture can reduce evapotranspiration and increase sensible heat flux. These effects would enhance atmospheric stability and inhibit cloud formation and precipitation generation. And in this following slides, we use 2 Sentinel simulations from 15 Earth models to assess the historical and future projected compound extreme events. The global negative correlation of soil moisture and VPD, as well as the bimodal distributions of soil moisture and VPD, are also found in these models, indicating that these Earth models can realistically simulate the compound extreme events. We use probability multiplication factor, PMF, to assess the increased frequency of compound extreme events compared to that if these 2 variables are independent. Compound extremes are defined as soil moisture below its 10th percentile and VPD above its 90th percentile. And PMF is defined as the ratio of the probability of compound extremes to that assuming independent distributions of soil moisture and VPD. High PMF is found in regions with strong correlation of soil moisture and VPD, such as southeastern US, Amazon, Southern Africa, East and Southeast Asia. Between the historical and future simulations, the differences of PMF is relatively small if we define these compound extremes according to simulations in individual periods. However, if we use historical thresholds to define these compound extremes, the PMF is projected to substantially increase in future simulations with the much larger range of the PMF in the figure C. And we also find large soil moisture variability for the regions with high PMF. Larger soil moisture variability can generate stronger impact on evapotranspiration and sensible heat flux, that lead to strong correlation of soil moisture and VPD and the occurrence of compound extreme events. This result is consistent with the idealized simulations that the soil moisture variability is largely responsible for the occurrence of compound extreme events. We also find the extreme high VPD and the low soil moisture become more extreme in future simulations. Both the threshold and mean values of the compound of extremely high VPD and the low soil moisture are projected to intensify in future simulations. The intensification of these compound extreme events have important implications for the capacity of continents to act as a carbon sink in the future. We then assess the impact of these compound extreme events on the carbon fluxes. We use 3 carbon indicators let ecosystem production AEP and its two components, gross primary production GPP through photosynthesis and terrestrial ecosystem respiration. Using observations from 66 flux tower sites, we find nonlinear GPP responses to VPD. When VPD is low, GPP would increase with VPD, but when VPD is relatively high, further increases in this VPD would lead to stomata closure and GPP reduction. Ecosystem respiration increases with VPD in a more moderate pace, and soil moisture depletion always reduce GPP and ecosystem respiration as water stresses lead to stomata closure and also limit soil enzyme activities. Under compound extreme conditions, in the top left beam of the right four figures, we find that the NEP decline in figure D is largely determined by GPP decline in figure B, while the ecosystem respiration is slightly reduced in figure C. And in Earth system models, the GPP anomalies during compound extreme events are also negative, except in boreal regions where GPP is enhanced, as boreal vegetation tends to be temperature limited. The compound event respiration is also enhanced in boreal regions, but slightly reduced in most other regions. The combination of GPP and respiration lead to negative NEP anomalies for more than 75% of the land grades for both periods. As I have shown earlier, the projected warming and drying trend and the land atmosphere feedbacks lead to much higher VPD and lower soil moisture extremes. This would result in strong negative anomalies of NEP in the 21st century. However, if we assess these compound extremes using historical threshold, the compound event GPP and NEP reductions during the compound event GPP and NEP reductions are still projected to intensify in the future simulations. The NEP anomalies during compound extremes are much stronger than that if only one of these variables is considered as extreme. So we assess the additional effect to represent the NEP differences induced by the compound extremes and soil moisture or VPD extreme only. The negative additional effect of extremely high VPD is much stronger than that of extremely low soil moisture in historical simulations. However, in the future simulations, the negative additional effect of extremely low soil moisture is projected to exceed that of extremely high VPD. And this strong effect occurs mainly in the northern hemisphere, but in Amazon and Congo basins, the negative additional effect of extremely high VPD is still stronger, as warming would greatly enhance respiration costs in these tropical regions. Here to conclude, the main messages of this representation include land atmosphere feedbacks lead to strong soil moisture VPD coupling and more frequent compound extreme high VPD and low soil moisture than expected if soil moisture and VPD were independent. The second, compound events are projected to become more frequent and more extreme and exert increasingly negative effects on continental production. The Earth system models project intensified negative effects of high VPD and low soil moisture on vegetation production, with the intensification of soil moisture exceeding those of VPD in the northern hemisphere. And thank you. I'm happy to take questions.
I'm going to ask a question. Not everybody in the audience will know what RCP 8.5 means. Yeah. Could you explain? And tell me why you chose 8.5 and not one of the others.
Actually, we choose RCP 8.5. One question is because we use the idealized simulations. These simulations are from a group in the European group. They use the RCP5. Oh, sorry. RCP5 means that the future carbon dioxide concentrations will increase, and the radiative effect of this CO2 increase will lead to, I think, the radiative effect is about 8.5. Yes. Sorry, I forgot the unit of that, but this is a lambda. And then because these idealized simulations use the RCP5 scenario, and so we performed future analysis in these simplified models, just want to keep consistent with these idealized simulations. And also in recent years, the CO2 increase follows the path of the RCP 8.5 scenario more closely than other simulations.
Okay. So I'm going to make a comment that I think is common in these types of things. RCP means representative concentration pathway.
Yeah.
The 8.5 is the number by which the radiative balance at the top of the atmosphere will change under that scenario, right?
Yeah.
Okay. There are very many scenarios, and RCP 8.5 is the most draconian. It makes a lot of implausible assumptions, including that the world population will reach 15 billion, which I think no sensible person thinks. It's common, the nasty character of the statistics of climate sensitivity is that the worst case scenario, which is what you've been talking about, is more probable than the best case scenario. It's a skewed distribution. But this describes the worst case scenario.
Yes.
Yeah. So it shouldn't be projected, and I'm not sure you did, as the most likely scenario. And I think this gets mixed up in the public's mind sometimes.
Yes, actually a lot of people, scientists also want to limit the temperature increase below 1.5.
Yeah.
Yes, so this 8.5 scenario must be worse than what we expected and what we tried to keep in the future. Yeah. So the projected impacts may be much worse than what we expected. But if we want to keep sustainability in the future, we must realize that if we don't keep the CO2 increase, increase in a more slowly pace than 8.5, we may get this result like this.
Mm-hmm. Okay.
Yeah.
That wasn't meant to be critical. It was meant to be a clarification.
Thank you.
I think you mentioned this, but the same models that you're analyzing show an increase in vegetation productivity in general. So this phenomenon that you're identifying of a decrease due to these extreme events is opposing the general increase, but doesn't overwhelm the increase in vegetation productivity. Is that right?
Do you mean the vegetation productivity?
If you just look at NPP in the same Earth system models, they all show an increase. Right, so you're identifying a decrease during extreme events.
Yes,
that's not enough to overwhelm the general increase that is coming about during all the other times.
Oh, so you mean the vegetation increase during normal conditions, I mean, may offset this extreme event? Yeah, I can check, but in this research, I just checked the GPP NEP decline during compound events, and that value compared to the mean values. But I'm not sure how would this compound extreme decline would be offset by GPP increase, because this GPP increase may be enhanced by CO2 increasing during favorable conditions. Yes, I understand. but I'm not sure whether, maybe, but in my opinion is that because more frequent and more intensified these compound events would offset this photosynthesis effect of CO2 increase.
Well, that can't be the case, because if that was the case, if you just looked at like the 20-year averages at the end of the century that a former EI postdoc did,
Yeah.
if this effect won, you would see a decline in NPP in the models, because it would be included in there, but you don't see that.
Yeah. But I have to assess that effect. Any other question?
Are there any questions for any of the other speakers that you may have thought of in the last hour or so? Okay, thank you.
Thank
so I'm going to wind up quickly and thank all the speakers and thank Samantha Ostrowski, who is, I'm director of the postdoc program, but in fact, Sam is director of the postdoc program. I'm sort of, I chair the admissions committee, and apart from that, I'm sort of the benevolent overlord of the program, and Sam is the go-to person that makes it run. So thank you very much. One thing Sam does is chair the admissions committee, and we are just about at the very end of the admissions process this year. It takes ages. It shouldn't, but it does. So we'll have a new group of people who you'll be able to see, maybe not in the fall, but in the next spring. We enter something like 6 or so students, postdocs, each year. So the standing cohort is 10, 12, which is quite a reasonable number of people to make a nice cohort. If anybody in the audience is a PhD student who's thinking about a postdoc program, come talk to me, and I can help you a little bit with information about the program. These programs work by combinations of people and combinations of funding sources. So just about everybody in the postdoc program has a mentor. We require that they have mentors who looks after them, and in many, many cases provide some funding. So they've got some skin in the game, so they want things to happen with the postdocs. And just to emphasize again what I said before, you'll see more applied type research in the postdocs than you will in the PhD program, which tends to be more theoretical. And this is the first time a lot of people get to use what they've learned in practical settings. So I hope to see you in the fall, where we'll do the next one of these with different people. Probably not in this room. Maybe one with better acoustics, but not as beautiful. So thank you all for coming, and hope to see you again.